Okay, thank you very much. I'm really glad for this invitation. I'm glad that you have a space like this for us to share our research. And for me, that I'm an undergraduate student, it's a great experience. So thank you very much. And thank you for to everyone who is in the other side of the screen. I'll be glad to answer your questions at the end of this presentation. So, well, I'm going to start. My topic is the synthesis and study of 2D materials. I'm working in my research project at the Laboratorio de Nanomateriales y Nanotecnología, that is the Nanomaterials and Nanotechnology Laboratory from the Universidad Iberoamericana. First of all, I'd like to tell you that this research, it's a teamwork. Felipe Cervantes Sodi is my professor, and some other students that are working at the lab are Said Sanchez Games, Diego Altamirano Tobar, Jose Luis Aguilar Charfen. They are my co-workers, and I don't know if some of them is here tonight, but well, this is also their work. Tonight, I'm gonna talk to you about what are 2D materials, the transition metal dichalcogenide monolayers, and then the method of synthesis that we use, it's chemical vapor deposition, and also a salt-assisted chemical vapor deposition. And then we are going to talk about the results of two of the TMDs, of two of the transition metal dichalcogenides that we are working on. We are also working in some others, but I'd like to tell you only about these two materials. Okay, so what are 2D materials? 2D materials are a kind of nanomaterials, and they are really important because among the applications of interest of this type of materials are the optimization of charge transport in solar cells, light-emitting diodes in the field of optoelectronics, semiconductors in transistors, photocatalysis, and among others. There are also applications in medicine, so we have a lot of things to know about these materials and find more applications. And on the other hand, the study of this type of materials has led to discover new physical and chemical properties due to confinement in 2 dimensions, different from those present in a bulk material. But again, what are 2D materials? 2D materials are crystalline structures composed of one or a few sheets of atomic thickness and large areas. You can see here in this figure. And also, we can find these structures that are 3-dimensional structures. And the thickness of these materials is what gives its name of 2-dimensional materials. The main 2-dimensional structures are the graphene family that you can see here, mexins, metal oxides, and transition metal dichalcogenides that we are going to see later. But look, there are many other nanomaterials in 2 dimensions that we can study. So I really like this topic because it's huge, the amount of materials. Well, okay, I forgot to tell you that some of the 2D materials can exist in nature in the form of stacked layers, such as graphene in graphite or molybdenum disulfide in molybdenite, that are prairie stones, from which individual layers can be exfoliated by different methods. Among its main features are the interatomic interactions in the plane, and are much stronger than those that occur along the stacking direction. These weak interactions are the van der Waals bonds. here in this text. Okay, well, now I'm going to tell you about the transition metal dichalcogenide monolayers. These kind of materials are semiconductor materials with the formula MX2. M is a transition metal that you can see here in blue. And you can see that we have 16 different transition metals. And we have 3 chalcogen. So we have a lot of combinations to study. Its crystal structure is made up of 2 layers of chalcogens and in an intermediate layer of transition metal. Here we have the 2 chalcogen and the transition metal. Some of the properties are strong spin-orbit coupling, the direct band gap. Unlike the indirect band gap of the bulk material, we have a direct band gap in monolayers. And another properties are, for example, for photoluminescence. And well, the synthesis method that we use is the chemical vapor deposition. This is a process to manufacture thin films of different materials, and these materials are synthesized through the chemical reactions of gaseous molecules containing the atoms necessary for the film material. In CVD, the elements that will make the material travel in the form of volatile molecules. So we can see here in this figure. And these molecules are denoted as precursors. This is the main material that we use at the beginning of the synthesis. And the film is constructed through a series of chemical reactions between precursors and the substrate. We have the substrate right here. We have main gas flow. We have the precursors that with high temperatures are in gas phase. And then precursors molecules are often diluted in this carrier or drag gas that constitutes the main part of the gas volume in this process. This is a process that involves the reaction of one or more volatile precursor present in a chamber. These chemical reactions take place on the surface of the substrates and in many cases also in the gas phase, like this. Then we have nucleation and island growth that I will show you later how it looks, and disruption of film precursor. And also what we don't need in our substrate, then is a disruption of volatile surface reaction product. We don't have these particles in our substrate. And we have an atomic step growth. Here. To improve the quality and increase the area of the synthesis materials, we use a salt-assisted chemical vapor deposition. The CVD method we use is by conversion of metal oxide, oxide by sulfidation or selenization to a TMD. We have here our precursors. And well, the salt function as seeds that promote lateral growth. As I told you before, we could see the nucleation here. These little tiny white spots is what we call the nucleation. And the salts function as seeds that promote lateral growth, giving continuity to the layers of synthesis. Also, the salt reduces the vaporization temperatures of the reactants, promoting the formation of oxyhalides as intermediate product, which have a lower melting point, and also increases the reaction rate, since the salts increase the mass flow. Here, the mass flow determines the amount of the metallic precursors present in the formation of the nucleation, which in turn determines the size of the structures forming the substrates. If we have more nucleations, we are going to have bigger triangles. These triangles are the material that we are synthesizing. So if we have more seeds, we have bigger and more triangles. Okay, the main parameters in CVD salt-assisted method are the precursors. Well, this depends on the material that we are going to synthesize. The precursors will be a metal oxide and a chalcogenide. It is important to emphasize that the position of the substrate are also important in the realization of the synthesis, being a parameter to be defined from the experimentation. So we have to do a lot of experiments to know where to put our substrates and our precursors. Then we can also change the type of salts, and this depends on the type of oxyhalide that is sought to be produced in the intermediate reaction. It is the type of salt that must be chosen. So here, for example, we put a salt, and we have an intermediate reaction that this is the one that reduces the vaporization temperatures of the reactants. So we have to choose wisely the type of salts, and this is also something that we choose from experiment and from reading some other experiments. The amount of salts, it's also a parameter really important, and the ratio in the mixture between metal oxide and salts will modify the mass flow of the precursor. And the gas flow influences the mass flow of precursors. The gases used primarily for CVD are hydrogen, nitrogen, or argon, and sometimes we also do mixtures of those gases. And also, as I told you before, when we use salt, we change the temperatures, and depending on the vaporization temperature of the precursors, we are going to use the temperatures. Okay, and also the distance between the precursors and the substrates is going to be an important parameter. And now I'm going to show you one of the experiments that we've been doing. This is the molybdenum disulfide. I'm not going to talk to you a lot of what this structure is. This was made with density functional theory. This is also a part of my project, but it was a lot to talk to you today, so I didn't want to talk about this a lot. So, well, for this experiment, we are using 100 milligrams of S. This is for molybdenum disulfide, yeah. And we are going to use, I'm sorry, I think I'm losing my connection. Oh, okay. Okay, I think I can hear you. Okay. Well, we are going to use sodium bromide as a salt, and we are going to use only one part of the salt and 10 parts of the oxide. And this is really a little of these precursors. So we are not going to use a lot like we use from S. So we have to define the temperatures, and we are we are going to choose it also by experimentation. And we are using a kind of substrate that only it's polished in one side. And also we are, in this experiment, we are only using argon. And this is our results. This is like the best results we had. We see these triangles that the sizes are 20 micrometers. But if we see at a scale of 100 micrometers, we can see that we have a lot of triangles, a lot of deposition of these layers. And also, if we see a 500 micrometer scale, we see that all of this part, I don't know if you can see my arrow or circle here, but here, this part, it's all the material that we wanted to deposit on this substrate. And well, these are same micrographies. And this is an atomic force microscope micrography. And with this micrography, we can see the seeds. These white dots are the seeds of this experiment. And also here, we can see in this photoluminescence micrography, we can see that all of this part is a layer, a continuous layer. And that is what we are, that is what we want to synthesize. And now we, in this experiment, we wanted also to have a continuous layer of tungsten diselenide. And you can see the biggest difference here is that we change the flux. We change here from a low flow, no, sorry, from a really high flow to a really low flow, because we don't want the precursors to move too fast and it can be deposited in the substrate. So we have to do several changes. Sometimes we also have to move all the systems so the precursors have the best temperature for the synthesis. And as a result, we also have big triangles and a lot of deposition in this substrate or this wafer. And here you can see that we have a scale of 1 millimeter. So in this sample, we had a lot of deposition. So we think that this method, this salt-assisted method, it's really useful for producing monolayers or a few layers of a material. And here, this is a photoluminescence micrography, and you can also see again these seeds. And something that I wanted to tell you is that we are still working on doing better experiments. Here you can see that we have different colors. And for example, here we don't have any deposition, but in this part we have a lot of layers. We can see that because of the change of the color. So what we want to do, what we need to do is to make few layers in these experiments. And also in this experiment, you can see that we don't have a lot of layers. Here we see that this is an orange color, and this is a red color. So we have here few layers, and we have here a lot of layers. And we want to have this kind of results. Also here, we want to have this kind of results, only a few layers. This is also an optical micrography. And in this one, we can see that we have a lot of material in our substrate. So, well, we are going to work in a better method. We want to use this method to synthesize more TMDs. The next step is to transfer the good samples to new substrates. So we can do Raman microscopy with other universities here from Mexico. And we'd like to study more of these micrographies with AFM and STM microscopes. And well, we only have to keep working and don't let the pandemic to stop us again. And well, I think I went too fast. I'm sorry. So if you want me to go back to some part, please tell me, and I'm happy to answer your questions. Sorry, I didn't. Is it in the chat? Okay, okay. What was it again, please? Okay, okay. What was it? Oh, I'm sorry. I opened the Twitch. It started to sound. Okay. Well, how do we assure that that happens? Well, actually, in some of the experiments, we have a lot of oxide in our samples, but we have to change the flow rate or the positions of the substrates and the precursors. So that is really an experimental part to assure that we have the complete sulfidation or salinization. Mm-hmm. Yeah. Not different types. Well, maybe sometimes we could have, for example, a forest of nanowires. Yeah, so it depends on what we are looking for. So, but all the parameters are variable. So we cannot use the same temperature if we use different salts, because of the temperature will change. Yeah. Yes, yes, a lot of variables. Well, we have to do this kind of micrography and AFM micrography, so we can measure the height of these triangles. So in this experiment, the height was about 15. Yeah, it was about 15 nanometers. So it was about 5 layers. So yeah, we have to study this with an atomic force microscopy. Yeah. Yes, it is possible, but it's a lot of experimentation. So as I told you before this transmission started, we only have been working for 6 months. After the pandemic, we only have 6 months at the lab. So we are going to keep working. So we can have a monolayer. So if you want, I can tell you later. Yeah, when we have that monolayer, I'll be glad to tell you. Yes, yes, exactly. And yeah, and also, as I told you at the end of the presentation, we want also to do Raman spectroscopy because of with the Raman spectroscopy, we can know more about the properties of the material. So as I told you here, we have different properties for a monolayer and different when we have more layers. So, for example, I was reading earlier that for one layer, we have a huge band gap. So we can use it for transistors, for example. But if we have two layers, that same band gap will reduce. And if we have more and more and more layers, we have a bulk layer, a bulk material, and then we have a non-direct band gap. So it changes a lot of properties depending on the number of layers. Yes, it's really great. Yeah, it depends. It depends on the mass flow. So sometimes we want to change temperature at a constant rate. So we have to let the reaction, the highest temperature of the both precursors for 5-10 minutes. And also sometimes if we let it more time, we have a constant layer. But also, if we are not careful enough or let it a lot of time, we will have oxides, and the sample will be contaminated. So yes, yeah, yes, these white spots. Uh-huh. Those are oxides. Those are oxides, but with the temperature, they disappear later. So, mhm. Yes, yes. Well, we have to do a lot of experiments to have the right parameters. So I think it's not an experiment that can be reproduced in other laboratory. If the oven is different, the experiment will be also completely different. It's hard to reproduce. I think that it's the biggest limitation. Yes, yes. Actually, in the next months, we want to use a CVD liquid method. That it's like the 2.0 salt assisted CVD method. Yes. Thank you very much. So, yes, thank you.
think my microphone's been off this entire time. All right, cool.
No, actually, I'm listening to you.
Oh,
Yeah.
no, sorry, I meant for the stream. I don't think anybody on the stream could hear me.
Oh,
That's
okay.
okay. Sorry, guys. Well, I guess you can figure out which questions were being answered by by the answers. Oh man, that's all right. Thank you for a great talk. Like I said, super interesting, really cool work that you're doing. We'll definitely look forward to seeing it, seeing more of it, hopefully. Thank you to everybody for coming out, and please be safe this weekend. We have next week we have two researchers. I think they're giving two separate talks. Dr. Aaron States and Dr. Suzanne Jaggi from UC Riverside. But in the meantime, have a great weekend. Be safe. Get boosted if you need to. And we'll see you next week.
Well, thank you very much. I hope I can join you next week.
That would be fantastic. We'd love to have you. All right. So thanks, everybody. And we'll see you next week.